My name is David Van Vranken. I want to welcome everybody to Chemistry 51C. And you might have noticed that they just announced the 2020 Nobel Prizes in Chemistry early this morning. And so I wanted to take some time before our lecture to talk about what was that Nobel Prize in Chemistry all about. And it's fantastic. The Nobel Prize in Chemistry for this year was awarded to two women, Emmanuelle Charpentier and Jennifer Doudna. And so let's go ahead and talk about the origin of that Nobel Prize. What were they being awarded the Nobel Prize for? The Nobel Prize was awarded for their work to develop the CRISPR-Cas9 system into a powerful tool for genetic manipulation. And the CRISPR-Cas9 system is, I think it's common to super common in prokaryotes and archaea. And it's kind of like an immune system for bacterial cells that allows them to target unwanted DNA, foreign DNA from viruses or other types of organisms. So the CRISPR-Cas9 system is composed of two components that come from the bacteria. The bacterial genome expresses a protein called Cas9, and that's this blue protein over here that you can see. So this is Cas9. And it's also composed of genetically encoded guide RNA. So the DNA genome inside of the bacterium or microorganism, it gets transcribed into RNA. And Cas9 forms a complex with that guide RNA. And so any sequence that is encoded by this guide RNA serves as a template for targeting and cleaving foreign DNA, like the DNA that you find in bacteriophage, which are bacterial viruses, or any other sort of organism that tries to slip its DNA inside of that bacterium. This system will cruise around the cell and clip at a very specific site any foreign-looking DNA that matches that sequence. So that's an amazing system. And what Charpentier and Doudna were able to capitalize on is that you can use this as a tool for super precise cutting of DNA inside of cells. And let's go ahead and talk about something that's interesting behind this story. And that is that there is a massive patent battle that has been brewing behind this technology. The CRISPR-Cas9, really developing it as a tool, was pioneered by Charpentier and Doudna. Maybe I should reverse it, Jennifer Doudna and Emmanuelle Charpentier. And they patented this. For some reason, Vienna is in on this patent. I'm not sure if that was Charpentier's original institution. They patented this as for the use of genetic manipulation inside of different kinds of organisms. If you can introduce or transfect cells with vectors that will express the CRISPR protein or the Cas9 or those guide RNAs, then you can get them to specifically cleave at any sequence that you want. But they didn't originally demonstrate that this tool was useful inside of mammalian cells. And there was an investigator at the Broad Institute associated with Harvard named Zhang that ended up patenting this for use inside of eukaryotic cells, which includes human cells. See, nobody wants to chop up errant proteins inside of bacteria and cure bacteria of their diseases. We want to cure humans of their diseases. And so the big money here really is in genetic manipulation of human cells. And so what has happened now is that there is this patent battle that involves kind of gender lines and race lines and coastlines. It's like the West Coast and Europe versus the East Coast, the University of California versus Harvard, in every kind of a way. So it's starting to look like Zhang may end up getting the patent in the United States, which is where most of the big money pharmaceutical development the money is really spent for eukaryotes, which is the organism that people really care about. But I think that the awarding of the Nobel Prize to Charpentier and Doudna really was a statement about where does the credit go to for the development of CRISPR-Cas9 as a powerful tool. So that's kind of cool. So congratulations, Charpentier and Doudna. Great work. And Jang, you may become rich someday. I guess you'll get something too for what you've done here. Ideally, everybody would benefit, and University of California and the Broad Institute in Harvard would come to some sort of an agreement. All right, let's go ahead and come back to the content of our lecture for today. We've been working on electrophilic aromatic substitution, and we've been talking about the rates of electrophilic aromatic substitution on substituted benzene rings. That's what we really care about. It's kind of rare that you would take an unsubstituted benzene ring and want to add an extra substituent to that, because you can buy all of those products from different chemical companies. So if you take toluene, I introduced this idea that whenever you have two substituents on a benzene ring, you can describe the relative orientation of those two substituents. When they're next to each other, we refer to those as ortho. When they're kind of spaced by one extra carbon atom, we refer to that orientation as meta. And when they're on opposite sides of the benzene ring, we would refer to that as a para relationship. And what I pointed out to you is that based on the identity of the first substituent on the benzene ring, when you add a second substituent through electrophilic aromatic substitution, some substituents greatly accelerate the ortho and para positions. And then some substituents greatly decelerate addition to the ortho and para positions, so that by default, you end up, if you add a second substituent, adding to the meta positions of those substituted benzene rings. And so I want to go into more detail to try to understand why it is that you get these different rates of electrophilic aromatic substitution on substituted benzene rings. So if we come back to this, this idea that there's three different positions. So there's over here the ortho positions, over here the meta positions, and then finally, the para position, and then finally there's the meta positions. Let's go ahead and take a look at the consequences of substituting at those positions. I'm going to expect you, and anybody who knows that you took an organic chemistry course will expect you to be able to draw the Arenium ion intermediates that result from addition of an electrophile to a benzene ring. And it's these Arenium ions and the resonance structures that you draw that will allow you to explain how easy it is to form each of these substituted Arenium ions. So what I want to point out is that if we add over here to the ortho position of this benzene ring, one of the resonance structures that we draw has that carbocation, also called a carbenium ion. The carbocation is right next to the initial substituent Y if we add ortho to the Y substituent. And in this position, this Y group strongly affects the stability of that carbocation. So strongly affects the stability. So there's going to be a massive effect of the substituent when we add to the ortho position. Let's take a look at what happens when you add to the para position. Whoops! When you add to the para position of a substituted benzene ring. Because if we take these electrons here and add to the para position, there's lots of resonance structures we can draw. This first resonance structure that I've drawn doesn't tell you anything special. The Y group is kind of far away. So let me go ahead and draw out another resonance structure here. I'm going to take these electrons in this double bond, and I'm going to add them into that carbocation, and we'll draw a resonance structure for that, where we can see that this is the same molecule, it's just a different way to depict it, that when you add to the para position of a substituted benzene ring, whatever that substituent is at the Y position is going to have a very strong effect. So in this case, the Y substituent will have a powerful effect on the stability. So in this case also, because there's another resonance structure we can draw, where that carbenium ion, that carbocation, is right there next to the Y group, you can see that when you add para, that Y group is strongly going to affect the stability of the Arenium ion. So again, strongly affects stability. And what I mean is of the Arenium ion intermediate, right? So if Y destabilizes carbocations next door, this is going to be a sucky intermediate to generate. And if it stabilizes that carbocation, this is going to be a nice Arenium ion intermediate to generate. We're going to use the same arrow pushing down at the bottom here to show the addition of the electrophile to the meta position. The arrow pushing for adding to the para position and the meta position is the same. when I start off with this benzene resonance structure. And so when I draw this first resonance structure, again, the Y is very far from that carbocation center. So let's go ahead and draw some of these other resonance structures to help us understand. You need to be good at drawing. There's always 3 possible Arenium ion resonance structures. You need to be good at drawing them and trying to figure out which one best explains the effect of the Y substituent on the stability of that Arenium ion intermediate. So let me go ahead and draw out this other resonance structure here. And what I'm going to do is I'm going to push these electrons and draw some of the different resonance structures. Here would be one. Let me go ahead and move those electrons around the benzene ring here. And one of the other resonance structures I would draw would put the resonance structure here, but that's not really right next to the Y group, right? It's not the carbon that's directly attached to the Y. We're kind of one over from that. So I don't see a big effect of Y on that carbocation. There might be a slight polar effect through space, but not through resonance or anything. So let me go ahead and draw another resonance structure. I've got one more. There's always 3 possible Arenium ion resonance structures, so I'll move these pi electrons over, and I'll end up drawing a third resonance structure. And we see that in this third and final Arenium ion resonance structure, again, the carbocation center is not directly next to the Y group. So there's no way for Y to strongly affect the stability of this carbocation intermediate when we add meta. There's like it'll have a polar effect, but there's no way that Y can really, it's donation that you care about that can stabilize that. So in this case, we would say that the Y group, if you add to the meta position, right, it doesn't strong. If I come back and I draw this, try to emphasize this kind of relationship here between these 2 positions. So I'll say it doesn't strongly affect. It does have an effect. Carbocation stability. So it's the effect will be kind of a polar effect, kind of Coulomb's law, that kind of thinking you should apply. So this is important for you to be able to recognize and break down the effective groups based on whether they stabilize carbocations or whether they destabilize carbocations. So what is it? What kinds of effects would you expect to stabilize a carbocation? So the thing you really want to look for when you look at a substituent when you generate an Arenium ion intermediate is you want to check and see that substituent has a lone pair, right? If you see a lone pair, and I'm just temporarily highlighting these, that highlighting will disappear. If you see a lone pair on the substituent, you should expect that substituent can stabilize carbocations. The more nucleophilic the lone pair, the better that lone pair is at donating into and stabilizing the carbocation. So right here, when we have an amino group, nitrogen isn't as electronegative as oxygen. The lone pairs are very available to donate. We'll see this when we get into chapter 25, and that very strongly donates into the into that carbocation lone pair. I'm going to change the way I depicted this because in our sapling exams and in the problem sets, I've been asking you to make your arrows end on atoms and not on bonds. So I just want to change this for a second to make it look like that, to make it look like the arrow ends on the atom. It was perfectly fine for the book or for outside this class, but for sapling, I want you to draw arrows so that they end on, and let me change this other one as well, so that the arrows end on on atoms instead of bonds. So just so we're doing everything consistently. I don't want to have 2 ways for you to answer a question. I'd rather it always be one way. Okay, so if you have a hydroxyl group or an alkoxy group on a benzene ring, we're going to tend to want to add to the ortho positions or the para position because that leaves a carbocation right next to the oxygen lone pair. If you have an amino group that has a carbonyl on it, that lone pair on the nitrogen will stabilize the Arenium ions you get if you add to the ortho or the para positions. And even if you have chlorine, which is kind of electron withdrawing, the lone pairs on chlorine will make it so that you favor adding to the ortho and the pair positions, because when you add to the ortho and pair positions, the carbocation, you can draw a resonance structure where the carbocation is next door to that lone pair. Okay, so there is a class of substituents that don't have lone pairs on them that also favor ortho and para substitution, and that is alkyl groups. So methyl, ethyl, isopropyl, T-butyl, hexyl, cyclohexyl, alkyl groups, like these here, propyl, isopropyl, T-butyl, those alkyl groups stabilize carbocations because you know that more substituted carbocations that have more alkyl substituents on them are more stable than carbocations that have fewer alkyl substituents, that have H atoms on them. So alkyl substitutions, even though they don't have lone pairs, also favor ortho-pair substitution because they favor this kind of pattern right here. That's kind of like, I'll just write approximately, it's like a tertiary carbocation, right, by having that extra substituent on there. So whether you add ortho or whether you add para to the pair position, you favor, you favor having, I'm just trying to add a little pointer with a ball on it. You favor adding to the ortho or pair positions because that allows you to draw an Arenium ion resonance structure that is stabilized as kind of a tertiary carbocation. Okay, what about there are some substituents that favor meta-substitution. And so really the way to think about these is that ortho and para are bad. That's really the effect we're mainly seeing. Everything is bad, but ortho and para are really bad. Let's try to understand why they're so bad. If I add here to the ortho position with my electrophile, so here's my electrophile, it's added to the ortho position of this benzene ring, and I've generated an Arenium ion. One of the resonance structures I can draw puts that carbocation center right in here next to the N+ of that initial substituent. So you do not want to have a trimethylammonium substituent and add to the ortho or the pair positions. So by default, you end up adding to the meta positions. It's slower, but at least it's not as slowed down as the ortho and pair positions. Likewise, and notice how there's no lone pairs on this N+. It's not the fact that it's a plus so much, it's the fact that it has no lone pairs. So the N+ does matter, but it's really the fact that it's missing a lone pair. We come over here and we look at a nitro group, super common functional group on benzene rings. And when you have a nitro group on a benzene ring, it has no lone pairs and it's an N+. So again, you super slow down addition to ortho and pair positions because they really are slowed down the most. And the meta positions are also slower, but they're not slowed down as much as the ortho and pair position. So by default, for trialkylammonium or some protonated amine, if it's an N+, you're going to end up substituting meta. It's going to be slow, but that's the only place you're going to see substantial rates of substitution. A sulfonic acid functional group is also going to substitute meta because ortho and para are slowed down so much more. And then finally, esters, aldehydes, ketones, amides, any kind of carbonyl group that's on a benzene ring, if you manage to get a substituent on there, you're going to substitute on the meta position because it is slowed down the least. So I expect you to be able to draw out these kinds of Arenium ion resonance structures. So let's go ahead and take another close look at the carbonyl group, because you don't see really a positive charge on the sulfonic acid group or a carbonyl group. But let's try to remind ourselves why a carbonyl should just be kind of similar to having an N+ on there. Let me try to do this in my black pencil drawing thing here. Let me go ahead and draw out an Arenium ion. What Arenium ion would I get if I started off with a carbonyl substituent of some kind, like a ketone on here, and then I tried to add to a double bond that was here connected to the ortho position? If I add the electrophile, I'll end up with an Arenium ion resonance structure that looks like this. But I want to remind you, and this is going to be super important when we get to chapter 20, chapter 21, chapter 22, that there's another resonance structure that we can draw for carbonyl groups. Let's go ahead and draw that resonance structure, because the resonance structure we would want to draw would take the electrons from the CO pi bond and give them to oxygen, because oxygen is more electronegative. So when we draw out this resonance structure that helps us to think about carbonyl groups, and a resonance structure that will be important for carbonyl groups when we get to these later chapters, that resonance structure would put a negative charge on oxygen because it's electronegative, and it would leave an unfilled octet, a positive charge on carbon, and only 6 electrons. So if you try to think about what would I not want to have next to a carbocation, another carbocation. That would suck. Oh my gosh, that's awful. So it's not like there's an N plus in the normal Lewis structure we draw for a carbonyl group, but this important resonance contributor to a carbonyl. It's like 25% of the character of a carbonyl is like this carbocation with an alkoxide on it. So this is clearly a bad resonance structure, and this is why a carbonyl is a little bit like a trialkyl ammonium, like a nitro group on there. So with aldehydes, we want to carbonyl groups, esters, we want to add the next substituent to the meta position. Okay, so there's two different. This is always the most confusing thing, I think, for people, and that is there's two possible effects that you can have when you have an oxygen or a nitrogen substituent attached to something. So one of the effects that you can have is the effect of electronegativity. It's kind of like a polar effect. Pluses and minuses interact through space, and they through a coulombic kind of effect. But there's a second effect that's important, and it's not the same. It's a completely different effect that you have to assess which one is more important. And that is that lone pairs can donate, resonance donation. Resonance is different from this electronegativity polar effect. So let's go ahead and talk about those, because you need someone like me to step in and tell you which of those effects is more important. And I'll just tell you, it's the resonance donation effect that's more important. So if you have an oxygen, an alkoxy group or hydroxy group next to a carbocation, oxygen has more protons in the nucleus than nitrogen, and that has more protons in the nucleus than carbon. And this is reflected in the electronegativity. As you walk across the periodic table from boron to carbon to nitrogen to oxygen to fluorine, all the atoms are about the same size. The only thing different is how many protons are in the nucleus. Oxygen has so many protons in the nucleus, it's got a lot of positive character, and so all that positive character hates being next to a carbocation, a carbenium ion, this type of carbocation center. And it's no different when you're attached to a benzene ring, an Arenium ion that has a carbocation, the resonance structure that has the carbocation next to oxygen. There is a destabilizing effect of having electronegative atoms next to a carbocation. You can't erase it. It's there. It's destabilizing. But at the same time, because oxygen has lone pairs, we're not talking about the nucleus of oxygen, we're talking about the electron lone pairs on oxygen. Those lone pairs can donate into that, and again, let me depict this so I'm making the arrow end on the carbon atom. This arrow ending on the bond is fine, but again, in sapling, we're asking you to draw every mechanism where the arrow ends on the carbon atom, just because I don't want there to be two ways to answer a sapling question. So this resonance donation is so powerful at stabilizing the carbocation that it outcompetes the destabilizing effect of the electronegativity of the protons in the nucleus. And that's the same effect you see when there's an alkoxy group or a hydroxy group on a benzene ring. Those lone pairs are so powerful at stabilizing it, donating into the carbenium ion, the carbocation center, that overall, it's better to have an alkoxy group on a benzene ring if you're adding substituents. They add faster because the lone pairs are so stabilizing towards carbocation centers. All right, we've reached a critical point here. I'm going to summarize all these effects in a table where I've taken away all the resonance structures and all the Arenium ions and all of that business, and I've just given you a kind of graph or a table here that summarizes all that information. And you have to memorize that. You have to memorize this table because there's an order to the substituents that I've drawn here, and nothing other than memorization is going to allow you to predict exactly the order of everything on this table. So here's what I've done. What I've done is I've tried to summarize the situation where we have a substituted benzene ring, and which substituents favor substitution at the ortho and the para positions, and which substituents favor substitution at the meta positions. And at the same time, I've summarized on this table which substituents make further electrophilic aromatic substitution faster, and which substituents make addition of more substituents slower. It's all summarized on this table. So the first thing that I've done here is I have ranked everything in this table from substituents that speed up electrophilic aromatic substitution versus substituents that slow down at the bottom electrophilic aromatic substitution. And so this whole list of substituents goes from the fastest rates to the slowest rates. If you have an amino group here on this benzene ring, if you have an amino group here, that's really going to speed up the addition of the next substituent through an electrophilic aromatic substitution reaction. Or likewise, conversely on the bottom, if you have a nitro group on your benzene ring, it's really going to slow down the rates of electrophilic aromatic substitution. So everything is ranked, and you have to memorize this order. You couldn't divine through some knowledge of electronegativity and resonance donation. There's no way you could have predicted exactly the order I'm giving you here, so you have to memorize it. Okay, so I'm comparing everything here to just a simple benzene ring, so where the only substituent on there is a hydrogen atom, right? If R is an H, that's just a plain unsubstituted benzene ring. Everything above this line, those substituted benzene rings react faster. We refer to those as activated benzene rings. And if you brominate it, nitrate it, do Friedel-Crafts, the reactions occur faster than they would on benzene ring. And the fastest ones would be if it's substituted by an amino group or a dimethylamino group. Everything below that line, we would refer to those substituted benzene rings as deactivated. If you have a fluorine, chlorine, bromine on your benzene ring, it reacts slower. If you have a carbonyl group where it's an ester, an amide, an aldehyde, a ketone on there, if the carbonyl is directly attached to the benzene ring, it's deactivated, and so on down the line to a nitro group. And then finally, we want to talk about regiochemistry. And the thing that it just kills me here that makes an otherwise easy table to memorize a hard table to memorize is the fact that when you predict ortho-para substitution versus meta substitution, the dividing line is almost the same. The things that activate are almost the same as the things that give ortho-para substitution. And here's the distinction. It's right here along this border line. Let me go ahead and actually I'll change into some sort of a glorious blue color here. So everything across this line here, this other line separates everything above that line, including halogens, which slow down further electrophilic aromatic substitution. All of the substituents above that blue line favor ortho and para substitution. It's faster to substitute at the ortho and para positions than it is to substitute at the meta position. Everything below the line, it's slowed down so much at the ortho and para positions that by default you're left over with meta substitution. And it's this dividing line at the halogens that really makes this table tough to use and memorize. So everything above the red line is faster, everything below the red line is slower, but everything above the blue line is ortho-para, and everything below that line undergoes meta substitution. Generally, the ortho-para substitution, you should assume that you get about 1-to-1 mixtures of products substituted ortho and products substituted para. And I realize there's statistically twice as many ortho positions, but there's a little bit of steric hindrance there. And so, it's hard to predict the exact ratios of how much ortho do I get versus how much para. So you should simply assume you're going to get about 1-to-1 ratios of those two products if you nitrate a benzene ring with one of these ortho-para directors on this. Okay, so you have to memorize this table. You have to memorize it because I'm going to ask you to predict. I promise you, I will ask you that. Every instructor in every Chem 51C third quarter organic chemistry class will ask you to memorize and use this as a tool to predict the products of reactions. So when there's already a substituent on a benzene ring, we refer to that as the effects of that on regiochemistry as a directing effect. And so we would say, for example, that a nitro group is what we would refer to as a meta director. And so I want to talk about what that means because some of you are going to have a tendency to get confused. It'll be the middle of the exam, you're going to be panicked, and it's going to be like, nitro group is a meta director. Okay, I have to take that into account. Here's the mistake that you're likely to make. It's one of the most common mistakes that I see people making. And you need to work enough problems where you don't make this mistake. Nitro groups are meta directors. They're at the bottom of that table that I told you need to memorize. What does that mean to say a nitro group is a meta director? Here's what it doesn't mean. It doesn't mean that the nitro group is going to go to the meta position. If you think that, then you misunderstood what the term meta director means. So a nitro group as a meta director does not mean that the nitro group is going to end up meta. That's not what that means. What that means is that the nitro group, if it was on there first, directs the next substituent to go to the meta position. That's what it means for something to be a meta director. So saying that a nitro group is a meta director means that if you start with the nitro group on there, the next substituent will go to the meta position. Let me just remind you of our recipe that we use here. It will be chlorine and ferric chloride, FeCl3 would be how you make that work. So, right, if you did take, let me just, this is wrong. I have to remember to cross this out, right? This would be the wrong prediction, saying that a nitro group is a meta director. So let's go ahead and, what would you get if you treated this with nitric acid, with our, with nitric acid in sulfuric acid with our classic nitration conditions. So the product that you would get if you nitrated this, the way you solve this problem is you have to memorize what's the directing effect of a chlorine group. And a chlorine group slows things down, but it's an ortho paradirector. And so you would get two products out of this reaction. The products that you would get in the reaction would be ortho, and I'll put the next substituent ortho. So if you use nitric acid in sulfuric acid. And the other product that you would get in about equal amounts, a 1-to-1 ratio, would be the para-substituted product. And again, just assume that they're present in a 1-to-1 mixture. So again, if you're nitrating a chlorobenzene ring, what you need to know is the directing effect of chlorine, not the substituent you're adding. Okay, I'm almost never going to ask you lengthy synthesis problems where there's no substituents on the benzene ring, or where there's only one substituent. Maybe I might ask that one substituent, but the real challenge is figuring out, when you're adding more and more substituents, what's going on. Now we have to come back and try to understand something special about Friedel-Crafts reactions. This is Friedel-Crafts acylation and Friedel-Crafts alkylation. Those reactions have special rules, and the special rule that I need to give you is that you can't do Friedel-Crafts on a ring that has a meta director. It really has to do with deactivating effects, right? If benzene rings have to have a certain level of reactivity in order for that to work. So anything that has that is on this activation list, anything that is at halogens or above, right? In theory, well, not anything. I'll come back and qualify that rule. God, there's so many rules with the Friedel-Crafts things. So you cannot do Friedel-Crafts with anything below that is a meta director, because it's too deactivated. So I'll just write down here, anything that is a meta director, no Friedel-Crafts. And I'll just write here parenthetically, it's too deactivated. It's just too, those substituents on the benzene ring deactivate the pi electron so much you just can't do Friedel-Crafts. So no Friedel-Crafts. But there's, in other words, if I ask you to make this compound that has a carbonyl group and a nitro group on it, you actually can't do the transformation. You can't synthesize this compound by starting with nitrobenzene, because, right, if you draw out the reagents, like, let me just draw this in black. If you draw out the reagents for this substitution pattern, the acyl chloride And remember the catalyst for that? It's aluminum trichloride. So if you draw those two reagents, this actually wouldn't work. If there's a meta director on the benzene ring, like a nitro group or another carbonyl group or a sulfonic acid, you're going to end up with no reaction. Nothing would happen. It's not activated enough to work. There's one more annoying, super annoying rule that you have to remember, is that when you have dialkyl amino groups on your benzene ring, these are the most activated benzene rings, you also don't see Friedel-Crafts reactions occurring. And it's because the lone pairs react with the Lewis acid. God, that's annoying. So in other words, it's only if you have alkoxy, amido nitrogen atoms, alkyl groups, and halogens on a benzene ring. Those are the substituents, the mono-substituted benzene rings that you can have where you can do a Friedel-Crafts acylation or alkylation. So how would you make this substituted meta-nitrobenzene derivative here? Well, it is possible to make it. You just can't start with nitrobenzene. What you do is you start by putting on the acyl group firsts. You take benzene and add an acetyl group through a Friedel-Crafts acylation first, and then you can add the nitro group. The nitration reaction has no special rules like about how active a ring has to be. So, and our recipe here is nitric acid and sulfuric acid, right? If you acetylate the benzene ring first, then you can add the nitro group, and then you can make that. So the Friedel-Crafts reaction just has all these special exceptions that you need to memorize, and I've always found that annoying, and maybe you would find that annoying just like me. But it just makes what ought to be an otherwise easy to use set of rules into one that's kind of hard. Okay, when you have let me come back, at the top of this list, we have amino groups and hydroxy groups. And they are, if you have an alkoxy group and an amino group on a benzene ring, it is really activated. It's not as active as just a regular carbon-carbon double bond, but as far as benzene rings go, those pi electrons are way more activated than a regular benzene ring pi electron. Okay, so this leads to some special problems. So you can do chlorination in the presence of ferric chloride on phenol, and phenol is more activated than an O-methyl group. But if you include the Lewis acid in here, the reaction is so fast that you can't stop it at a single chlorination event. So the only way to get this to stop is you just leave out the ferric chloride or the ferric bromide. If you want just one substituent on your phenol, and this is specifically if there is an OH on here. So not if there's an alkoxy group, you get more control out of that. So if you have phenol and you want to add just a single bromine atom, you can't control ortho or para. You get a mixture of those. Then leave out so you leave out the ferric bromine catalyst and you just treat it with Br2, and you'll get substitution. The Br2 doesn't add across double bonds to add two bromine atoms. That's not the way those reactions work. So you get substitution of an H atom. So if you want just one halogen substituent, which is really, you would want one substituent. You don't want to put three substituents on the same ring. That doesn't really help you. With anilines, they're just so souped up. They are so reactive. If you have an NH2 or two methyls on the amine, or a methyl and an H, those are so super reactive. They're the top of our activating group list. There's nothing you can do to stop. No matter what you do, whether you include the ferric bromide or exclude the ferric bromide, you're going to get overbromination in these cases. You can't stop it, those reactions at a addition of a single bromine atom. So now notice I'm dividing this up where I treat this as an independent case here. Whoops, let me change back to my black pen here. So if you start off with a nitrogen substituent that is a carbonyl, we don't call those amino groups anymore. What we're going to learn about later is we have a completely different name for these kinds of functional groups. We refer to that as an amide. Doesn't matter what the other R group is. A nitrogen that is a carbonyl group isn't even called an amine anymore. We call that an amide. And so that you can brominate just one time easily. In fact, we used to do that in our organic chemistry laboratory course that we take alongside this. I don't know if they still do that. We used to synthesize parabromos, the parabromo compound for acetanilide. through electrophilic aromatic bromination. Okay, I'm going to go ahead and stop right here. And when we come back on Friday, I'm going to talk about what happens if you have two substituents on the benzene ring. Because I gave you a rule. I said memorize the order of these activating groups. You have to memorize the order of those and memorize which ones are activated and which ones are deactivated. Right? It's important for you to know which ones react faster than a simple benzene ring and slower than a simple benzene ring. And I gave you this other line to know, which is which ones are ortho-para-directors, that's above the dashed line, and which ones are which of these substituents are meta-directors, and that's below the dotted line. And when we come back, I'm going to try to resolve this issue of what happens if there's two substituents on the benzene ring. How do you decide whether which of those two substituent is going to control the ortho-para-meta substitution pattern, the regiochemistry of the third substituent that you add? So when you've got two substituents, how do you decide where the third substituent ends up? So, okay, work sapling problems. I extended the due date for the 51B practice stuff to Sunday, I think, because we had problems getting our sapling website going. And also due on Sunday evening at 11:59, right next to midnight, is the chapter 18. So you have to be working these problems in sapling and finish that assignment on this weekend before Monday starts, because we're launching into new material on Monday.